Hello, I am Mauricio Mendoza. This is Real World Field Trials. This was made by Ezequiel Martinez, Alejandra Rodriguez, and me, Mauricio Mendoza. Background and motivation 8051s, these microcontrollers, they're very powerful, they're very cheap, and they have a lot of resources on board, but compared to some other devices that we have now, they're not as hefty. A computer can run AI inside the computer. It's a lot harder for an 8051 to run it, but there is a way to do it. And the idea is that if we can get an 8051 to run AI, then we could implement them everywhere as nodes and receive information from them and predictions from them, and then use them as sort of tools in all sorts of different industries for all sorts of different things. So the idea is that we need to practice using these 8051s in the real world. Um, there's only so much testing you can do simulated on a computer. By testing them, we can correct for errors, for noise, missing data, outliers, whatever, and then also determine whether how realistic it is to use them in the real world. If in the simulation it behaves a certain way, but then you take it out in the real world and it's like way worse, maybe you shouldn't pursue that anymore. So the system overview, what we're going to do is that we're going to use the 8051s in every room, and each one is acting as a node, pulling in information and then sending it to a central coordinator, a computer, a Raspberry Pi, something like that. Something more powerful than an 8051 that can handle all these packets of information from all these different sources, and then that central coordinator can log it, make visualizations, and then also compare it to information it actually knows about the building, whether there's people there or not. We're going to be using the University of California occupancy detection data set. It comes with lots of different columns of this building, the lights of every room, the CO2, all sorts of different things. Light and CO2 are most important because we're only going to be using those two. I'll get to that in a little bit. And then the training set is split into the testing, the training, and I think it's more testing. And that will be our real world testing, is using this data set. Is we're going to train the AI with the training data set and then test it on the test data set. But all this data comes from real world scenarios, and so based on how it operates here, it's a similar reflection of how it would operate in a real world situation. So like I said, we're only going to choose light and CO2 because, as I said, an 8051 is limited. It has limited RAM, limited CPU, limited ROM. So we don't want to overload it with too many sensors. We can't load it with too many sensors. And so we're only going to be using a light sensor and a CO2 sensor to pull in light and CO2 data. And then the algorithm we're going to make that can create predictions is only going to use a depth of 2. The decision tree is only going to have a depth of 2, again, to conserve RAM and CPU. In this way, we still have presumably enough sensors to predict whether or not a room is occupied or not. And then it's also enough that we don't overuse the 8051 and maybe push it to its bounds. We don't want to do that because then that's when errors start to come in and maintenance is more required and all of that. So the way we're going to be doing this is we have a Python program that will create the algorithm for us, and it's going to do all the training, all the testing, and it creates the algorithm for us, and it puts it in the header file, a C code header file, and it's going to export that to us. And so with that header file, we can upload that to the 8051 along with an actual C file. And with that header file, the 8051 knows what metrics determine whether or not there's somebody in a room from its sensors. And The idea is that the Python code is very powerful. So the Python code is run on a computer that can actually run the Python code, and it'll export that header file, which is a lot smaller and a lot less heavy. So an 8051 could actually handle the header file. So like I said, the Python file, it trains with these big numbers. It outputs these big numbers. So we need to scale them down to 8 bits so that we can actually put them inside the 8051. Otherwise, the 8051 wouldn't be able to handle them. So we scale them down, and they're completely preserved. All the main ideas, all the main features are completely conserved, but it's not so big that it'll destroy the 8051. The algorithm in our main C file is this one here. This is what determines whether or not there's somebody in the room. Some prediction algorithms are recursive, which means it calls on itself until it breaks. These have the chance of looping infinitely, which would be okay on a computer, which have like safety nets and stuff like that. But on a 8051, it's stack based, and so it could break itself. It could cause all sorts of crazy errors, and lots of maintenance would be required if we use a recursive based algorithm. So that's the benefit of using non-recursive based algorithm, a for loop. So that's what it means by stack safe. And this algorithm is actually very good because it only uses less than 13% of the RAM. So the rest of the RAM is available for all sorts of other things. So the way we're going to be using this, in the real world, in actual deployment, the idea would be to hook up two sensors to the 8051, one for CO2 detection and light detection. So if there's a lot of light in a room, that means there's probably somebody there, coupled with the idea that there's a lot of CO2 in the air. That means there's probably somebody in there breathing a lot, exhaling a lot of CO2 and using light. If there's no light in a room and CO2 levels are low, there's probably nobody in the room. And the way the 8051 would know these things is with a sensor. And so the 8051 would take in these things, quantify it, make a prediction, and send it to the central coordinator, whatever it would be. And the central coordinator would do the stuff. I'll get to that later. But for the field testing, the simulation of the field testing, we're using dummy variables since we don't actually have the sensors on us right now. And so with these, we can try and simulate what the sensors would say and see how the 8051 would operate with dummy variables, which would simulate real sensor inputs. There's also a timer portion of the code in the 8051. This is so that we can keep track of how long it takes for each prediction to be made, because it's making inferences at a certain frequency, and so that frequency is determined by the timer. So the timer starts when it starts making an inference and stops when it stops making the inference. And then we also have a timer checking how many cycles it took per frequency. And then all this information is packeted and sent to the central coordinator. So the central coordinator can then decide how efficient are all these different nodes. Is one node a lot less efficient than the other ones? Is one node a lot more efficient? Why? And then the person taking maintenance could go and see why one node is maybe a lot slower, a lot faster. This is what I was talking about. We're using UART packets, and this is how we're doing it. So we're including the features, the ID, the verdict, whether the node thinks that there's somebody in there or there isn't, which node it is. That's the identification. The ticks, how long it took to make that prediction. And then this is also just for error checking if any of the values are wrong or whatever. This helps to correct it. And so it sends this information as a packet to the central coordinator, who then logs it, digitizes it, and visualizes it. And so that whoever's manning all of this and observing all of this doesn't have to go to each node on its own. It just goes to one, either like a tablet or something, and can see all of this digitally. This is, again, what I was saying, that the sensors feed to the 8051, and then the 8051 sends it to the central coordinator. network coordinator visualization is what I was saying. The network coordinator takes in all this information, and then it knows what's actually going on in the building, so it can compare what the 8051s think is going on versus what's actually going on to make error detections and accuracy and see how good it is, basically. And also just for actual implementation, it could be used to see what the sensors are saying. If there's people here or there, what are they doing? This is a simulation of what our results would come up with, showing that this would be a very good results, that the predicted is actually a little bit ahead of the actual, or sometimes exactly on it, and it's matching the actual numbers, that there's actually somebody there when there actually isn't somebody there, etc. Over here too, assuming correctly the number amount of people, small errors. And then also this would be very good numbers to receive from actual implementation, would be low average latency across a couple of days from all the different nodes. This is assuming we only use 10 nodes, possibly for 10 different rooms in a building. If a building had 50 rooms, we would need 50 nodes, but less nodes is preferred, more manageable, more maintenance friendly. But yeah, if the latency was low, how long it took to predict, that would be really good. And the energy and duty cycle operation, given the code and the 8051's limitations and whatnot, it's inferred that per inference, it would take up about 20 microjoules of energy. And so depending on the different battery, they all kind of decay at the same amount. But at even high inference rates, it does go down as more inference rates, because basically you're saying, I want the machine to do more per second. Is basically it. The frequency is 10 to the 4 is I want it to do 10 to the 4 frequency, meaning I want to check hundreds of thousands of times per second. And then a really low frequency would be just like 10 times a second. So obviously only using the device 10 times a second would mean that it would last a lot longer than using it a lot more per second, like hundreds of thousands times a second. But even at hundreds of thousands of times a second, you have a very long battery life, because again, the 8051 is very small, requires very little power, and the algorithm is very efficient. So, and we are only using 2 sensors. It's only using 20 microjoules, and these batteries are very advanced batteries. It would still last a very long time, very long amount of hours. If this were to actually happen, this would not be a good result. If we deployed these 8051 nodes into a building and we started seeing the decay in accuracy as the days going on, a linear decay in accuracy, then within a month we would have to replace it, do something, change the code. This is not what we would want to see, but this could be what we would see. And so if this was seen, then maybe there's a bug in the code. Something's going on. We would have to go see what's going on. So we would need to map this and the way we would map this is by receiving all the information from the packets to the central coordinator. The central coordinator would create this map by comparing the predictions against the reality. And every day, let's say on the first day, everything's at optimal percentage, it would be a 98% correction. Of 100 rooms, it correctly predicted 98 of them as being what they actually are. And then 2 of them, maybe they were empty, but it predicted that there was somebody in there. But then at this trend, at day 50, it would start predicting 50 of the rooms incorrectly, and you don't want that. So cross-platform comparisons and scalability. Again, this is if it's not working. If it was to work very well, then these are the strengths of the 8051. Low battery life. Again, it lasts a very long time, even at very high frequencies, at high inference frequencies. And then it's a legacy, so they're like everywhere. Everybody knows about them. Very low income countries, they're aware of an 8051. They're in everything they use. and they're very popular. They have low accuracy, as seen in the previous one, so maybe you would want to tone down the amount that you use, because if the accuracy starts to decline quickly, if you have 1,000 of them, it's going to be hard to repair all of them, update all of them, whereas if you only have 10 of them. Um, and the latency is considered kind of high. It was still okay, but compared to these other better microcontrollers, these have a lot smaller latency, much better accuracy. The only drawback is maybe that they're a little cheaper, a little more expensive, and that they require a little bit more energy, but still not impossible amounts, such that this could not be implemented with a Cortex or an ESP. But again, what we had available to us was an 8051, and that's why we chose that. And then this is again, showing 8051, a lot worse than these other two. As I said, as the number of nodes increases, they're going to be a lot less reliable. There's going to be so many, the central coordinator can't manage them all. You would need a lot more central coordinators, and then you would also need to manage a lot more central coordinators, which would all need to, it would be a big mess. But the Cortex and the ESP don't have these issues, again, because they're a little more expensive, and they have a bit more they have higher reliability. These are some findings from our research, some similar case studies of projects done like ours. Smart building occupancy, again, checking if there's people in rooms and floors for HVAC, lighting optimization, etc. Crop monitoring, you would want to set up soil moisture sensors, humidity sensors, CO2 sensors on the field to determine how are these things doing, these metrics. And so if the CO2 is too low, you would want to go in there, increase it so that the plant could do well. If the soil moisture is really low, you would get a ping from the central coordinator, and it would say, oh, a node over here is detecting low moisture, and you could go and fix it. And so you would ensure efficient plant life and no wasted seeds or anything like that. Wearable worker safety, industrial wearables with physiological environmental sensors, site enterprise scale, hazard detection, fatigue alerts, compliance monitoring. So this would be like every employee on like a job site wearing a node, and that node would read information off of them to see if maybe their heart rate is too high, call the on-site medic to go and maybe do a physical or something like that on them. Tell them that they need to take a 5-minute break. Sometimes workers forget to do these things. Having a node on them that transmits their biosignals to a central coordinator could then ping for hazardous things and whatnot. These are some visuals of these different things. Lessons learned and best practices. We learned that although the 8051 is very small, very cheap, it's very robust, it's very good. There's efficient ways to execute even complex ideas like integrating a machine learning into the 8051, a machine learning algorithm into it. When experimenting with a data set of real world scenarios, we encounter different issues that you don't encounter with simulation and with concept. So that's also something we learned. And recommendations would be regular ground truthing, long-term node health logging, feedback for adaptive over-the-air updates. So like I said, maintenance-wise, it would be hard for somebody to go to every single node. So a good practice for the future would be if there was a way to make it so that the 8051 could be updated based on errors found virtually online and whatnot, so that somebody wouldn't actually need to go to that node. In this way, the number of nodes could be increased from a small scale of like 10 to like 50 for bigger buildings and whatnot, or 500. Conclusions and outlook. Real-world field trials prove that edge machine learning legacy microcontrollers is reliable, practical, and cost effective. Yeah, as I said, 8051 has been around for a very long time, and there's a reason for that. It's a very good tool, and it's just depends how you use this tool. The limitless. There's no limits for this thing's applications, and it's not the carpenter's a tool. So maybe you want to upgrade to something a lot more expensive, a lot newer edge. Not everybody's going to want to use those things. The low economy countries, they're not going to want to use those things. They're not going to have the information to know how to use those things. The entry level for those things is a lot higher, but an 8051, as I said, is everywhere. They're likely the engineers at these low income countries. They're probably familiar with an 8051, and so this case study, they could take it and use an 8051 in a similar way. And also for the future, automated model, maybe an algorithm that self-corrects. So if there's errors found between the real values and the predicted values, they could have an AI that goes in and corrects itself without a person even having to do it virtually. And then if this was the case and practice experimentation proved very successful, it could be applied to even large networks, like maybe multi-building infrastructure where there's a headquarters all across the country. They could all be connected to a single place, and that would be hundreds of thousands of rooms, hundreds of thousands of nodes, all sending information to multiple central coordinators, which then send to more central coordinators back home. And that is my presentation. Thank you for your time, and that's my time.